question number 1. When a person is pushing against a wall, what is the name of the force acting against the force of the push? The person is pushing, and something is pushing back. Thank you. And the question is, what's the name of that force pushing back? So you've all answered, and I hope the majority answer is the one on this one here. You recognize the handwriting. And that is, force pushing back is the normal force. The normal force is the force that is keeping something from going through a surface. So you push on the surface, you'd go through it if there wasn't something pushing back, and that's the normal force. Number 2, which of the following parts of a car can accelerate? You can see I changed the words halfway through. Can accelerate the car. So can the gas pedal accelerate? What is acceleration? Change in velocity over change in time. So we're looking for anything that can change the velocity, that is the speed or the direction. Can the gas pedal change the speed of the car? Assuming it's in gear, yes. Can the brake pedal change the speed of the car? Yes, assuming it's moving. Can the steering wheel change the speed of the car? No, but it can change? No, it can change the direction. So since velocity is speed and direction, these two here can change the speed. This one here can change the direction. So all of those were correct, hence the correct answer was E. Number 3, a Newton is a simplified unit that represents what combination of units? This one was probably the most difficult one on the quiz. Remember Newton's second law. This is the way I always remembered the units when I was starting out. Newton's second law says sum of the forces is mass times acceleration. What are the units of mass? Kilograms. There was no subterfuge here. It didn't have grams to confuse you. And then we have acceleration. What are the units of acceleration? Meters per second squared. So kilograms times meters per second squared. That one. And the final one. A combination of all forces that act on an object is called the net force. So the answer is BEBC. Any questions or comments about the quiz?
So if the question 2 would have asked something like, which one of these changes to speed only, then you would only say gas and brake.
Right.
Okay.
Right. And these are all questions that you came up with. This was 4 out of the 6 that I had put in for potentials for so far. So, you're getting a feel for what your classmates are writing as you go through this. On the exams, should be about half the questions come from you. Funny thing, because we only have 8 students, you'll probably have quiz questions very heavy on that part of the exam, simply because we don't have many more questions that we'll be using in quizzes. So the quizzes are a good study tool because you'll probably see a lot of those on the test. Okay. Any last comments before I go to the lecture formal? All right. So lecture, and here we go. So we've been talking about Newton's laws and forces. I've talked now reasonably extensively about the first and second law. Second law being what we studied in lab yesterday. So in lab yesterday, I gave a little bit of lecture on the second law, and then you studied it. What did you discover happened when you changed from having 4 washers to 8 washers? What happened to the acceleration? It increased. So you found that indeed the acceleration increased when the net force increases. Is that directly proportional or inversely proportional? Directly. You found that the acceleration was directly proportional to the net force. Notice it's not an individual force, it's the net force. In your lab, if you actually were to look at that cart, What are all of the forces that were acting on the cart? Okay, you had the force of gravity. What else? There's still a force normal because it wasn't sinking through the track. What else? Go ahead, Danny. Okay, you had a force due to the mass hanging here. I'm going to remember we talked about Newton's second law. You have to define what your system is. So I didn't make a big deal of it in class yesterday or in lab yesterday, but the best way to treat this problem is to actually have put the excess washers on the top so that you have the mass between all of your washers and the cart stays the same, and then actually make your system all of this, not counting the pulley. So there, pulley disappeared. Make that entire thing your system. It makes life the easiest, but there's a little technicality here that can be confusing. We have a string. Uh-oh. What'd I do with my little bob with the string on it? It's my second favorite demonstration. Oh, here it is. Okay. Whew. Can't live without this. My second favorite demonstration. I go with the simple. So when I had this, when it's hanging, I have the string and I have the bob. If I look at the bob, the forces on the bob are gravity down and tension up. Tension is the name of the force produced by the string. But tension is just the force that's distributed by the string. And so in an ideal world, remember we have an imaginary world of introductory physics. In that imaginary world, wind doesn't matter. So in the imaginary world, if I drop this, the air is not going to slow it down. In reality, the air is going to have a very small effect on this, on the bob. If instead I were to drop paper towel, the air has a significant effect. So sometimes that imaginary world premise of the wind has no effect makes sense, and sometimes it doesn't. And we'll talk about that later today. Another imaginary world thing we impose in physics is that the string has no mass. Of course, the string has mass. Mass is a measurement of how much matter is present, right? There's matter here when you don't have a string. But the mass of the string is very small compared to the mass of the stopper, and so we make the approximation that there's no mass. In that case, then the tension in the string is the same everywhere. That is, the force that is being transferred through the string is the same everywhere. And it will put a force on whatever touches it that's equal to that tension, pulling away from it. So on the bob, since the string is pulling away upward, the force of tension is upward. On my hand, what direction is the string leaving? Downward. So the tension is making a downward force on my hand. And so basically what the string is doing is making it so force-wise, it's like my hand is holding the bob. Then we have the pulley. Let's imagine that my finger is a pulley. So I put my finger here. If it's a pulley, the pulley can rotate freely. We make some more improbable assumptions. We say the pulley has no mass since it has no inertia, because mass also measures inertia. Hence, there's no resistance to changing the rotation of the pulley. And we say there's no friction on the pulley. If there's no friction for the pulley and no resistance to rotation, then it's not going to affect the tension at all. And so all the pulley does is change the direction of the tension. So in our system, we can say, okay, all the pulley did was change the direction. So it's the same as if I straighten out. Okay. That's the wrong button, that's why. I straighten this out and I just have my bag with the washers here pulling with a force, and I'll put W for washers, that's going forward. We know the gravity was actually pulling down, but all the pulley did was change the direction. So I take out the pulley and make it so it goes forward. There was one more force. What's that one last force that we want to ignore? I believe I heard somebody say, there's the force of friction. The tracks have a fairly low friction, so we ignored it. We ignored a lot of things in physics, don't we? When you get to real life, you can't ignore these things. In fact, the people who make the hardware and software we use in lab, that's Pasco, Paul A. Stockstead Company. He's a Seventh-day Adventist. He gives us a nice, good discount on his equipment. So I like to make sure I give him his fair due for giving us some discounts. They actually proclaim this is better than a no friction situation because the students see reality. They see there really is friction. That car is going to stop over time. Of course, in our physics world, we pretend that's not the case. Okay, so we have this picture. And so if you look at the net force, remember in class yesterday, I said we can separate the vertical from the horizontal and just look at the horizontal motion. And so I only looked at the horizontal motion, and the sum of the forces in the horizontal direction, which typically we call that the x direction, was the force of the washers minus the force of friction, which we approximated was 0. And so for your experiments, this was a 10-minute soliloquy on why for your experiments, the net force, we only looked at one force because there are only two forces in the horizontal direction, and we said the other one's approximately 0. So I don't want you to have the impression that force is mass times acceleration. That's incorrect. Net force is mass times acceleration is correct. And so in this case, the net force was just one force. So yes, that was a pretty long way of getting to that important outcome that many people, like our textbook, often ignore and just say, force is mass times acceleration. Let's not confuse them. Just like he says, let's use 10 instead of 9.8. Let's not confuse them. I think it confuses more to be incorrect. Okay, then what happened when you put the bar on there? When you doubled the mass, what happened to the acceleration? Okay, the acceleration dropped. And so was that proportional or inversely proportional? That was inversely proportional, which means it goes in the denominator. So in the end, you verified this equation. Now, you didn't do many tests. It's not proven correct. If you did a lot more tests, would you prove it correct? No, you wouldn't. Danny, I'm going to ask you specifically because you're the only one that was brave enough that I saw to say no. Why wouldn't you prove it correct if you just did lots and lots and lots of experiments on getting second law?
If you prove something correct, you prove that your ideas or your thesis is incorrect.
That's right. In science, we can prove things are incorrect. We can show that the prediction doesn't work, so it's incorrect. But if it does work, there could be other factors involved. So we didn't prove it was right, but we can prove things incorrect. So you get more and more and more confidence, but the scientific process is never done. You never are like, woohoo, we proved it, now let's move on to something completely different. You can say it is considered settled. It would be crazy for us not to believe it, but you don't say it's true, right? You say we're confident in it, but we didn't prove it. Now going to free fall. We've already talked about free fall. There were two questions asking about the definition of free fall from last class period, so don't ask that again, okay? If I have something falling and there's nothing affecting it but gravity, we call that free fall. Is it truly free? No, there's gravity affecting it. But it's free from everything except gravity. As long as we're earthbound, we can't be free of gravity. So we call that free fall. Now, if I have an object in free fall, here's my object. What forces are acting on it, according to what I just said the definition of free fall is? Gravity, and that's it. See how the force of gravity, which is mg. And then we can take Newton's second law and say, well, the sum of the forces is mass times acceleration. Since there's only one force here, the sum of the forces is just that one force, and I have mg equals ma And it does not take a mathematical prodigy to say, oh, look, I could divide mass from both sides, and then it cancels, and I have the acceleration is equal to g. That's why we call g the acceleration of gravity. That's the acceleration any object will have if it's in free fall, because of Newton's second law. And so the acceleration of gravity, g, 9.8 meters per second squared, it has a direction, it's a vector. The direction is down, because we define down as the direction of the force of gravity. So if something's in free fall, it's always going to have that acceleration of g, which is 9.8 meters per second squared, with the direction of down. So here's just a practical example, basically what the whole Leaning Tower of Pisa thing was. You have one brick, two brick, red brick, blue brick. So you have these two bricks. One is one brick and one is two bricks. You drop them. Do they have the same downward force? No, they don't. Ashton said that. No, not the same downward force. The one that has two bricks has 2 times the mass. Hence, the force of gravity is 2 times the mass times g. It has twice the downward force. How do the accelerations compare? They're the same. They're in free fall, so I said that they're always going to be the same. But you say, but there's more downward force on one than the other. How is it going to have the same acceleration? Because Newton's second law says the acceleration is the net force divided by mass. So the downward force on the one with 2 bricks is 2 mg, but then you divide it by the total mass of 2m, and the 2m's cancel again, and you're left with g for the acceleration. So that's what the whole thing for Leaning Tower of Pisa was to show. It doesn't matter what the mass is. You're going to have the same acceleration because the mass cancels out. Now, that was before we had Newton's second law. But it was showing that the mass didn't matter. Okay, the first of our clicker questions.
What channel?
It is channel 33, or if you're using your smartphone, web SCNC. A 5-kilogram iron ball and a 10-kilogram iron ball are dropped from rest. For negligible air resistance, that is, no air resistance, the acceleration of the heavier ball will be, and I must have done something wrong because it's not telling me how many answers I have for each one. We'll see what happens when we're done. Did you set the channel?
It just won't turn on.
Oh, it won't turn on. Yeah, well, that would be a problem. Okay, Ash is getting logged in. All right, let's get.
Usually I push the channel and it works, but it's not.
So everybody change the contrast. Even if something should be shown. Sorry. You know, my gut feeling is throw it against something, but that's bad. Bad feeling. Still logging in, Ashton?
Almost there.
Okay.
It worked.
Yeah, what?
It worked. I just had to change the channel.
Oh, right. Yours has. I just need to register that as yours, and it'll be fine. Or, well, it at least is recording them. We have to figure out how to get the scores to me, but
Okay, I got it.
not yet. Oh, you logged in.
Yeah.
But you don't have an answer yet. Okay. Of course it didn't show me what you answered. Why would it do that? Okay. Well, it didn't show me the answers again. This is not just my problem. Everyone across campus is having this problem. New software, new bugs. Company says, what? There shouldn't be that. Okay. What answer did you all choose? Thanks. The same. Because it's what I was just talking about. The mass cancels out. You have acceleration is equal to the net force divided by the mass is equal to the total mass times g divided by the mass is equal to g. Okay. Now, what happens if you drop a boulder and a feather at the same time? We've done lots of goofy things like this. Unfortunately, my demonstration for this is no longer working, so I can't do the demonstration here in class. That is, my tube no longer holds a seal. But let's answer this question. When the air is removed by a vacuum pump and you drop a coin and a feather, so we remove the air. In this case, there really is no air. So there really is no air resistance. Then does the coin and the feather fall at the same rate? So they hit the ground at the same time. Does the coin hit first or does the feather hit first?
It says it's not open.
It says it's not open. Okay. I swear it said it was open. Okay. It's open now. Meanwhile, my linky here don't work. I'm just gonna switch over to show the video. Okay, Ashton Stowe. Okay, please work this time. Yay! Sorry, I had quit just before you said that. Don't break it. Okay, let's watch a little video nothing here that's going to be violating your privacy rights. To see this in action.
Well, in my left hand I have a feather. In my right hand a hammer. I guess one of the reasons we got here today was because of a gentleman named Galileo a long time ago, who made a rather significant discovery about falling objects in gravity fields. And we thought that where would be a better place to confirm his findings than on the moon. And so we thought we'd try it here for you.
So instead of
The
vacuum
feather
chamber,
happens
just
to
go
be
to the moon.
appropriately a falcon feather for our falcon.
The land.
And I'll drop the two of them here, and hopefully they'll hit the ground at the same time. How about that? Mr. Galileo was correct in his findings.
And then you jump around because, hey, you can. And let's not watch any more YouTube videos. So I think it's kind of fun to see actually done on the moon, something we definitely can't do here in class. To see, hey, it does work just the way I said it would, because I wouldn't lie to you. Once again, though, why do we have lab? Because you shouldn't just take things on faith. You should demand that there be some evidence for what you believe. So, when I jump out of an airplane, which I don't do, right? I don't jump out of an airplane with a parachute either. I've got this healthy fear of landing hard. But I do have experience snow skiing. And I was on a ski trip once and I was racing a student. And when you want to race, what do you do to go as fast as you can? Yeah, you get down your little tuck because you want to hit less air. If you hit less air, you're more aerodynamic, which means you have less air resistance. And so I got in my tuck and I was blowing this kid away. Now I had some advantages, right? I had some big old 203 skis. I always skied on longboards because that's what was popular when I was in high school. And so I had these longboards and I had a lot more mass than the kid, Jason Wong, if you care who it was. And so having more mass, I have more downward force, and the force of friction that's opposing that, there is friction between your skis and the ground, is roughly the same And so basically, I had more downward force with the same upward force, giving me a net force that was bigger, and I had a bigger acceleration, and so I was just blown away. We get down to the bottom, and sadly, there was just this little roller at the bottom of the run. And I am flying here just in front of the ski lift, and I go over that roller just thinking, you never do anything on those. And I went flying, and I crashed, and I had to go walk back up the hill, grab my ski. I put my ski on, and he passed me as I was putting my ski on. That's how far ahead I was. So I lost. So the next year, we're on a ski trip again, and Wong says, let's race again. All right. And so I get in my tuck, and you know what happened? That crash hurt a lot, and I was scared now. And so I would start going fast, and I'd feel, wow, I'm going really fast. I could fall again, and I would stand up. And when I stood up, what happened? I could feel myself, getting pushed back and really slow down. Then I'm like, I'm not going very fast to get back in my tuck, and so I was tuck, stand up, tuck, stand up. He beat me because I was a wimp that time. But the air resistance was real and made a difference. If you jump out of an airplane and you go spread eagle, that air will slow you down so that you're going to be going somewhere less than 100 miles an hour. Is it going to feel good to hit the ground at 100 miles an hour? Most definitely not. Probably going to be fatal. But you have a chance. What if, on the other hand, you say, look, I'm a javelin? Then you're going to be going really fast because you have much less air resistance. The ground will definitely not be your friend. And of course, people who use parachutes, they have something that is going to be much bigger, thus give them much more air resistance, slowing them down much more because the air resistance increases with speed. And so you're going to slow down until the net force, the upward force due to air resistance and the downward force due to gravity, is zero. When the net force is zero, what happens to your acceleration? Okay, so if the net force is zero, then your acceleration is zero, and what does that mean for your speed? Your speed's going to stay constant. So you reach what we call terminal velocity, which is the constant velocity reached when the net force is zero. And so here you have a picture. This guy has a bigger mass because he's built like me. And so he's going to have a bigger downward force, which means he's going to go faster so that his air resistance gets bigger as well until they balance. So he falls at a faster speed. So if Danny and I go skydiving, we have exactly the same parachutes, I'm going to hit the ground a lot faster than Danny will because I weigh a lot more than Danny. It's not fair, is it? No. I wouldn't either. So we would both be in the plane saying, what are you crazy people doing jumping out of a perfectly good airplane? Okay, now Newton's third law. Newton's third law, the one that's summarized by, for every action, there's an equal and opposite reaction, says that in that statement, how many people have heard the statement for every action there's an equal and opposite reaction? Okay, everyone. In that statement, action means force. So you rephrase it in the more traditional language, and it's for every force, there's an equal and opposite returning force. Now what this means is if I put a force on Rachel, so like I said yesterday, we now know that we can make force and distance from gravity. If I put a force on Rachel, I push on her bandana. According to this rule, she has to push back on me with a force that's exactly equal. So the harder I push on the bandana, the harder it pushes on me, but in the direction that's exactly opposite. That's Newton's third law. Now that has some real simple implications. Let's say you do something really stupid like get in a fight. And so I throw a punch, and boom, I crack somebody right up here where the head is really hard. My hand hits their head. It's going to put a force on their head, right? Their head is going to put a force on my hand. You know it's going to put a force on your hand. You know it's going to hurt, right? Which force is bigger? The force of the hand hitting the head or the force of the head hitting the hand? I got one answer. Okay, we have a couple people say the hand. That is what most people say. But Newton's third law says they are the same because they have to be equal and opposite. So no matter how hard I hit somebody in the head, their head is hitting my hand just as hard. Now a sad but true fact. The bones in my hand are not as strong as the bone right here in the head. So if I punch somebody here in the head, have the same force on the head and the hand until we reach the force where something breaks. And what breaks first? Bones in my hand. Now it's going to hurt their head. Sure, their head may snap back and cause them to have some brain injury. Brain injuries are bad. But it's also going to cause me real damage. Now, of course, I don't espouse fighting. But if you are going to hit somebody, you at least want to hit them somewhere that's not as strong as your hand. So, I'll hit like this. Then you just are putting a shear force on these bones in the jaw might break before your hand does. But don't fight. That's a better rule, right? What I always like to point out is headbutting. In the movies, people headbutt all the time. In reality, if you were to take your forehead and hit somebody else on the forehead, so forehead on forehead, those are two pretty much anvils. You're going to have a really large force and both people's heads are really going to hurt. Now, one person might have been prepared and had all their muscles tight so their head doesn't snap, and the other one wasn't ready, their head snapped. So there can be a difference in the outcome. But in general, both of you really hurt your head. So that's not smart. Now, if you have to headbutt somebody for some reason, I can't imagine the reason where I would need to headbutt somebody. You want to try to make something hard on your head, like your forehead, and something soft on their head, like the nose. Well, the nose breaks easily, right? I've had my nose broken a couple times. Playing sports, a ball hits you in the face, nose is broken, right? So if you hit their nose with your forehead, sure, it's going to gouge your forehead a little, but it's going to crush some cartilage and maybe some bone there on the nose, and so it's going to do more damage to them. But what's the bottom line in all of my statements here? Don't fight, okay? But Newton's third law says equal opposite forces. So let's put this into a practical example. Let's say that I have a big old truck. Whatever. Big old truck. And I have a little not so smart car. And they hit each other. How does the force of the truck, failed that one miserably. How does the force of the truck on the car compare to the force of the car on the truck? Leslie says they're the same. What possible reason could Leslie have for saying they are the same? Newton's third law. For every action, there's an equal opposite reaction. The smart car was hitting the truck, and so the truck was hitting the smart car. And the force of those two is exactly the same but opposite directions. But everybody tends to think it's probably going to be a bigger force in the car than on the truck. Why would they think that? Okay, there's a lot bigger mass on the truck, and the truck is built to a much higher strength level than the car. So the truck has a lot of momentum, a word that's coming up in one or two slides. It's hardly going to slow down hitting that little smart car because it has small mass, small inertia. And that smart car is going to change its speed a lot, and it's really going to get crushed because it's not nearly as strong as the truck. And we tend to say, well, the one that got crushed the most had the most force acting on it. Not true. It just wasn't strong enough and it crumpled. So it'd be the same force. So, yeah. Don't need to go over that. We've talked about all these things. It sometimes is hard to identify the reaction forces. Reaction forces have to be between the two same objects. So we have things like, I stand on a scale and I have a downward force due to gravity. What's the reaction force to my downward force due to gravity? Almost everyone gets this wrong, so don't feel bad if you say the wrong thing. I stand on a scale and I have a downward force due to gravity that's acting on me. What is the equal and opposite force that is paired with that downward force on me? It's not the support force. That's what almost everyone would answer. But it's not the support force. What's the force of gravity between me and, what is it again? It's not between me and the scale. The scale's not what is attracting me. It's the earth. The earth is pulling me down. And so the reaction force needs to be a force on the earth due to me. I am pulling the earth up, believe it or not. It's the same exact force, but you know what? The mass of the earth is so huge, it doesn't really care. So the reaction force to the force of gravity is the force of gravity pulling the earth up. So then where does the support force come? The support force is a reaction to my feet pushing down on the scale. My feet are pushing down on the scale is pushing up with an equal and opposite force. Question?
So the force is pushing up on the scale is coming from the earth? I'm confused on what you're saying.
Okay. If you look at me standing on the scale and you identify the forces, there's the force of gravity acting down on me, and there's the force normal acting up on me. Now, a key to why these can't be the reaction forces is the equal and opposite forces are acting on opposite objects. So the equal and opposite force to gravity has to be a force on something else due to me. And so the equal and opposite force to the force of gravity on me is the force of gravity on the earth from me. And the equal and opposite force for the normal force is going to be the force of me on the scale. It's not acting on me, it's acting on the scale, so it's not on my picture. Just like the force of me pulling up on the earth is not acting on me, so it's not on my picture. Because my picture is only showing the forces acting on me. So finding those reaction forces is kind of hard sometimes. We had a question, though, on our quiz where it was much easier. You're pushing on the wall. That's a force of you on the wall. The reaction force is going to be the force of the wall on you. So in that case, it was the support force. Okay, I'm going to skip over this because we only have 6 minutes left. Soccer player kicks the ball and exerts 1,500 newtons of force on the ball. How much will the ball exert on the kicker? Equal to 1,500, more or less? Actually, you know what? I will have you answer it because I've got to give Gabby a chance to answer a question because she now has a clicker working. Oh, wait. It says, what? I don't know. It said 7 responses. We didn't have any responses on this question yet. I have to document that. Gabrielle. There we go. All right. Everyone but Sam.
Says no link up on channel.
Everybody else did. Well, you've answered enough that you're not going to lose points. So there you go. Oh, and look, it took away all the answers for all. I love life. Well, the correct answer was, I should have just called on somebody and had them explain it. It's 1,500 newtons. It's equal in force. Once again, a lot of people think, well, I mean, the ball doesn't hurt your foot, so it must not hit your foot as hard. And the ball takes off and your foot doesn't. No, it's an equal and opposite force. Okay, this is the last slide on Newton's third law. Just showing places where this comes into play. Rockets are an example of using that equal and opposite force. The way a rocket works is the rocket has mass in it and it pushes it out. That mass was initially stationary. The rocket puts a force on it to push it out. But according to Newton's third law, that mass that was pushed out had to put an equal and opposite force on the rocket that pushed the rocket forward. I have to tell you, over Christmas break, actually it was on Christmas Eve, we were driving to my sister's house to celebrate Christmas, and we stopped for gas, and my sister's like, look behind you. And we got out and we watched the SpaceX launch. You guys seen those pictures? It was so amazing. We're like, I know it's not a UFO, but if you didn't know, you would think that was a UFO because it was pretty spectacular.
Wait, is it that thing? Because I saw a friend post like a video where it's like it showed this like weird colored thing. Like
Yeah, it was really weird because you had I didn't look at it until after they'd separated. So you have the rocket here, and it looks like it's shining this searchlight that's spreading out on this other object that's trailing behind. And then they're going like this, and then the other object turns red, which of course was its thrusters to send it back down. And goes. It was really bizarre. We're watching it. Okay, it was just really cool. Sorry. But that's a good example of Newton's third law. So now momentum. Momentum is inertia in motion. Inertia was a resistance to change in motion. So when we say momentum, we're talking about it's inertia in motion. It's moving. It doesn't want to stop. And we measure momentum with mass times velocity. The symbol for momentum is P. Momentum is mass times velocity. It's a vector. It has direction. So if you double, let's see if anything's going to work here. Okay. Nope, not starting the polling. Oh, hey, look, now it crashed. Well, don't worry about answering the questions because it crashed. Well, if you double the speed, since momentum is mass times velocity, what's going to happen to the speed or to the momentum if you double the speed? What should it do? No, really, the presentation stopped. It crashed. I don't know if it will accept anything, but okay, good. I mean, since it crashed, it shouldn't be. What would your answer be? Doubles. Good call. Because if this doubles, this is going to double, assuming m stays the same. Impulse is a funny term, one I actually don't like to use. Impulse is equal to the change in momentum. Delta's change in momentum is equal to the impulse. We don't have a symbol for impulse. We just write out the word, the rare times when I use it. And according to Newton's second law, it turns out that the impulse is equal to the net force multiplied by the time over which it's acting. This here doesn't quite look the same because it doesn't say net force, it doesn't say delta T. But the impulse is the net force multiplied by the time it acts. So I can have a small force like me pushing a car and a long time to get it up to 10 miles an hour. Or I can have a large force, such as we get from using the car's engine, and a small time to get it up to 10 miles an hour. It's the same impulse, it's the same change in momentum. It's just one is a higher force and less time, one is a lower force and a longer time. So this example, these two pictures are illustrating the same impulse. You have a truck that hits a haystack. I don't know if you've ever worked with hay, but if you get a stack that big, it probably actually is going to put a big force, but not as big as a wall. And so when the truck hits the haystack stops it, but it takes a while to stop it. And it's a smaller force. Whereas when the truck hits a wall, it stops it really quickly. Since the time is small, the force has to be big. Now this brings us to automobile safety. In your car, you have safety devices, things to protect you in the case of an accident. What are those safety devices? Airbags? Seatbelts? Okay, we'll stick with those, especially because of our time. The seatbelt was the first thing to put in the car, First, they just put the seatbelt on your lap, a lap belt. And then if you get in an accident, while your lap stays fixed with the car, but what happens to your head? It goes boom! And so your head comes really fast, and then it hits something like the dashboard or the steering wheel, and you cause major damage. That's not a very good safety factor. So then they put shoulder straps to keep your body from coming forward. And the shoulder straps originally were bolted in place, not good. Now they have little springs on them. So if you get in an accident, you pull on that shoulder strap and it stretches the spring. Why? Because it increases the time for you to stop. And if you increase the time for you to stop, it's the same impulse, it's the same change in momentum from your initial mass times velocity to zero, but with a larger time, you have a smaller force, so less damage. The airbags are even more of that. The airbags deploy, they come out at you at like 200 miles an hour. And then they stop and they have big holes in the back. And so it comes out and hopefully it stops before you hit it and you deflate it quickly, but not nearly as quickly as if there was nothing there. It extends the time, lowers the force, makes it safer. Okay, have a great weekend and a happy Sabbath.